Let's learn that it is possible to challenge everything, even issues that are widely accepted by society and even the greatest minds in history. Yes, even Einstein could be wrong, and through studying and researching, you can critique people like these great figures and point out their mistakes. Hello and welcome to Mr.Logicman's channel. This channel is created with the sole purpose of raising awareness, sharing scientific knowledge, and researching scientific topics. Everything that is said and discussed here is entirely based on reason and logic, because reason is humanity's greatest asset and what distinguishes us from other beings. I also apologize in advance for not having the perfect accent and possibly mispronouncing some words. I hope the interesting nature of the topics helps overlook any mistakes in pronunciation. Today we are diving into the fascinating world of special relativity and exploring what many consider to be Einstein's greatest mistake. Join us as we unpack these complex concepts and unravel the mysteries of the universe. If you're curious about how science and philosophy intertwine and want to learn more about the implications of relativity, stick around. Let's get started. First, I'll try to briefly present the views of some of the great philosophers and scientists on the topic we are discussing. Then, in the end, I will share what aligns with truth, reason, logic, and draw a conclusion based on that. Let's kick things off with Plato, who in Timaeus presents a captivating view of time. He sees it as a shadow of eternity intertwined with a higher realm of ideas. For Plato, time is cyclical, measured through changes of movements in the material world. He argues that the material world mirrors the world of ideas, suggesting that time and space depend on changes within this realm. In his view, time is a measure of cyclical changes and only gains significance when related to motion. Space, to Plato, serves as a backdrop for movement, intricately designed by a creator, often referred to as the demiurge. Ultimately, he posits that time cannot exist without the changes that define it, setting the stage for further philosophical exploration. As we move from Plato's idealism, we step into the realm of Aristotle, who takes these foundational ideas and builds upon them with his own insights about the nature of time and space. Aristotle. He asserts that time is dependent on the movement of objects, acting as a measure of change. His work not only expands on Plato's views, but also provides clarity on the relationships between these concepts. He defines time as the number of motion, emphasizing its existence only in relation to movement. This brings us to his categorization of time into natural time, which is linked to natural events, and social time, which is defined by human activities. This distinction echoes Plato's idea that time is tied to motion. Aristotle also notes that time progresses in periods, but individual movements are transient and fleeting, similar to the cyclical changes that Plato describes. When it comes to space, Aristotle views it as empty, defining it as the boundary separating objects. He challenges the notion of absolute empty space, asserting that every object occupies some space. This perspective is reminiscent of Plato's backdrop for movement, highlighting their shared philosophical groundwork. Finally, he explains motion as transformation defined through four causes: material, formal, purposeful, and efficient. This detailed breakdown not only reflects his understanding of movement, but also connects back to Plato's emphasis on the interplay between time and transformation. Transitioning from Aristotle's rich exploration, we encounter Newton in the 17th century, who revolutionizes our understanding of time and space with his groundbreaking work. Newton. In his mathematical principles of natural philosophy, Newton proposes that time is absolute and independent, marking a significant departure from philosophical musings of Plato and Aristotle. He introduces the concept of absolute space as a constant, unchanging void where objects exist, while still acknowledging relative space, which considers positional changes of objects. This shift emphasizes a more physical understanding of space, moving away from philosophical discussions of his predecessors. Newton views time as linear, uniform, and perpetual, existing independently of events. This perspective starkly contrasts with Aristotle's view that time is intricately tied to motion and transformation. His principles laid the groundwork for classical physics, guiding scientific thought until Einstein's theories challenged these long-standing notions. As we navigate through these evolving ideas, we encounter Leibniz and Huygens, who present contrasting perspectives on the nature of time and space. Leibniz. He argues that time and space are relative concepts defined by relationships among events. His perspective resonates with Aristotle's emphasis on the movement of objects as essential for understanding time and space. Leibniz famously illustrates that without objects and their movements, time and space lose meaning. This argument highlights the necessity of change to define both time and space, reflecting the foundational ideas we've explored. Huygens. In contrast, Huygens sees time and space as absolute categories. He focuses on the wave theory of light and believes in universal laws governing motion, asserting that time and space can be examined independently. This divergence creates a dialogue with Leibniz's rational view, showcasing the ongoing debate about the fundamental nature of these concepts. Now, let's consider the key differences that emerge from these discussions. Leibniz perceives time and space as relational, emphasizing the importance of change, while Huygens regards them as independent and constant. Their differing definitions of motion also have significant implications for the development of modern physics. Fast forward to the 20th and 21st centuries, where modern physics introduces new insights into time, space, and motion. Now, let's speak about modern physics and quantum theories. In this era, time is examined as a fundamental and variable dimension, with principles like Heisenberg's uncertainty shaping our understanding of subatomic interactions. Theories like string theory and quantum gravity aim to unify time and space, exploring these concepts under extreme conditions. The evolution of our understanding of time, space, and motion reflects profound changes from ancient philosophy to modern physics. Newton's foundational theories paved the way for Einstein's insights and contemporary scientific concepts, illustrating the complexity of natural phenomena that continue to be explored. This ongoing quest deepens our comprehension of the universe's fabric, challenging and refining our definitions of time and space. We've gone over all these theories to get to the main point of the discussion, and so far, we have just been talking about different ideas from famous scientists and philosophers. As I mentioned earlier, Einstein believed that no object can travel at the speed of light. According to his theory of special relativity, as an object's speed increases, its effective mass also increases. What this means is that the closer an object gets to the speed of light, the more its mass shoots up. So, to actually push something to the speed of light, you'd need an infinite amount of energy. And since getting infinite energy is impossible, no object can ever reach the speed of light. Einstein also stated that the speed of light in a vacuum, around 300,000 kilometers per second, is constant for all observers. This is one of the core principles of his theory of special relativity. He was so convinced about the unchanging nature of the speed of light that he argued if something were to actually travel at that speed, its speed would look different to various observers, which would totally go against the idea that light's speed is always the same. The most interesting and also most complicated outcome of special relativity is what happens as an object gets closer to the speed of light. Time for that moving object slows down, and the object itself shortens in the direction it's traveling. If anything were actually to hit the speed of light, these changes would become so extreme that they just would not make sense anymore. Einstein also believed that light, or more specifically electromagnetic waves, which include visible light, does not experience time the way we do. According to this theory, for example, when a photon of light leaves the sun, it takes about 8 minutes to reach Earth as we observe it. But because a photon moves at the constant speed of light, which Einstein thought was the ultimate speed, it does not experience time at all. In fact, it exists everywhere along its path at the same time, from the moment it is emitted from the sun all the way until it reaches our eyes here on Earth. So, in a way, it's like the photon is instantly present at both the sun and everywhere along its journey, right up to where we observe it. Now, let's take a closer look at this theory and point out some major flaws. To really understand the issue, we need to dig deeper into the concept of time and what it truly means. Let's begin with a simple example. Picture a table. This table has length, width, and height as its dimensions. Now, can you imagine the table without these dimensions? Or on the flip side, can you imagine the dimensions without the table? After thinking about it, it becomes clear that the table and its dimensions are tightly connected and rely on each other. A table or any object really cannot exist without dimensions, and dimensions only make sense in relation to physical objects. Time and motion, or more specifically, time and change or transformation, are connected in a similar way. Just like dimensions define the size of an object, time can be thought of as a way to measure change or movement. Here is the key idea. While objects and their dimensions are totally linked, the object itself kind of takes priority over the dimensions in terms of existence. In the same way, transformation comes before time, with time being what we use to measure that change. Now, let's get back to the main point. Based on these ideas, if we accept that a photon does not experience time once it is emitted and exists outside of time, we'd also have to assume it exists outside of space too. In other words, if there is no time, then there cannot be any change or movement. This would mean the photon exists everywhere and everywhen at once, which just does not fit with what we know and understand about how the world works. Following this line of thinking, a photon would need to exist in every moment of time and every place at once, but we know this isn't true. Let's break it down. Imagine a photon is created at 12 o'clock on the sun and then shoots off to Earth, arriving 8 minutes later. How can something that is created in time and disappears in time be considered timeless? That just does not add up and goes against common sense. At first, time includes the photon, and once it is emitted and becomes part of the flow of time, it seems to separate from it. But then, it is the photon that ends up interacting with time. How does that even make sense? When you look at it more closely, you will see that this perspective has some fundamental flaws. It just does not hold up. Now, let's dive deeper into the theory of special relativity. There is no denying that as speed increases, time slows down and that no object can actually reach the speed of light. However, at the speed of light, time does not just stop or disappear. That idea would only make sense if light were the ultimate speed in our universe. But time at this speed does not vanish. It simply slows down dramatically. In fact, If an object were to attempt to move at that speed, it might require a mass equal to or even greater than the total mass of the universe, rather than needing infinite mass. This basically means that the speed of light is the ultimate speed limit in the universe, not because it is the absolute fastest speed possible, but because time itself is what restricts anything from going faster than light. So, we can conclude that what is actually absolute is not the speed of light, but time. And if we ever try to surpass that speed, it is time that stands in our way, preventing us from going beyond that limit. In fact, Einstein's theory of special relativity presents deep contradictions and challenges in this regard, which can only be reconstructed and resolved through this particular perspective and explanation. So, with all due respect to one of the greatest scientists in history, Albert Einstein, the implications of special relativity at the speed of light are fundamentally flawed and do not really match up with the reality. Let's learn that it is possible to challenge everything, even issues that are widely accepted by society and even the greatest minds in history. Yes, even Einstein could be wrong, and through studying and researching, you can critique people like these great figures and point out their mistakes. Never be afraid of express your views and always strive to keep thinking, even if your ideas are met with laughter and ridicule. Many theories that are now considered undeniable truth were once mocked, just like Galileo and the theory, or rather the reality, of Earth's roundness. So do not let the fear of judgment hold you back from thinking critically and sharing your thoughts. Do not stop thinking and always prioritize logic and reason in your thoughts. I hope you enjoyed this discussion. I'm here to share what I've learned from many years of studying and exploring different fields. I would love to hear your thoughts, so do not hesitate to share your opinions. Do you really think Einstein cannot be wrong, or is he just human like the rest of us, and we should not put his theories on a pedestal? Until next time, when we explore more mysteries of the universe, take care.